So the agenda for the talk is, talking about the BI world and the big data world as being two different things in the organization, and how converging them is actually beneficial and optimal for the organization. And in order to do that, this idea of smart data is the missing piece, so to speak, in all of what we do in the enterprise. Yeah. And HitDime 2.0 is a smart analytics platform that actually is built on top of smart data, which is using semantic technology. And so the majority of the time, hopefully whatever is left of it, I would like to spend it on the demo, a working version of it. But it is an involved demo in that we are trying to do graph analytics and all of that stuff. So hopefully you'll bear with me. It may seem a little bit complicated, that there are a lot of things that are going on, but we'll see. Yeah, and please feel free to ask me questions. At the end of it or in the hallway, given that some of my time is taken away here. But quickly, just to introduce, HitDime is an offering from Lead Semantics. That is the company. I'm the CEO of the company. It's a startup about 4 years old. It's probably a little more than a startup now. We are Series A funded, and it's focused on semantics-driven data science. Much like cognitive data science, cognition and semantics, they go together. Something that addresses the human needs. Ultimately, whatever the machine learning, whatever that we do, one way or other has to be catered to the human being on the other end. No matter how much automated that we all get, at the end, the consumer is the human being. And that gap between whatever is produced out of automation, that last leg has to do with cognition and semantics. Semantics is the only known, practical technology to fill that gap. And we are specialized in that. Yeah, I'll just go on. So the two worlds of BI and big data, the top row, as you see, it's meant to do reports and dashboards. It sounds mundane, but it is involved, and it has established history, multiple decades. The multidimensional analysis is able to produce what is very important for decision makers, right? And the thing of it is that what all the decision makers are seeing in these charts and all these interesting visualizations, if they were to ask a question of why something is happening or how is it happening, and that's what led to this big revolution in big data. Folks had to look in all the data that is collected in the enterprise and had seen that all these logs and transactional data and whatever could be used for further analysis that could actually feed into enhancing your insights and so on. But that is the second row, if you will, the big data analytics of why it happened, and that led on to focusing on predicting what could happen in the future and so on. So it often is focusing on new, interesting, focused analytics, and but they all end up in PowerPoints and so on. Somebody has to kind of explain and convince powers that be, who are kind of used to seeing this in the established standardized charts and so on. So the idea is that the enterprise, even though the way it is being analyzed, all the data is two different ways, so to speak. Enterprise is one. I mean, all the data is one single world. All the data and the different types and all the scale and computing that the enterprise has, it's like one single resource set, and that all has to be factored into the insights that the company will draw out. And then only you get a sense that you are actually making sense of everything that is happening, all the money that is being spent. Right? The goal of enterprise analytics is to process all data, no matter what the technique under the sun may be, all data, and then produce the right insight at the point of decision. That ought to be the catchphrase, right? It's not about how fancy the analytic may be or the technique. What is coming out, is it actually getting into the business decision workflow that leads the decision makers to make the best decision. Yeah. So the goal, I mean, it's sort of I'm restating this, is try and merge these two lines of activities, so to speak. And we need to imagine or reimagine the data side of it, being that a lot of it has to do with how the data is being collected, how it is housed, how it is fundamentally treated in the organization, because of the number of different transformational steps that it has to go through, feeding into all these activities, be it in the big data line or the regular BI line, has to do with a lot of moving and churning the data, and all of that is causing a lot of I would say inefficiencies in the organization. So rethinking data would probably be the first step, and it turns out that is the way that it can actually enable you to actually converge these two workflows. So that's what our pitch, our company has staked its claim, and it has completely staked its future on this thing called semantic technology and smart data. Yeah, and we propose, and our products are built on top of this. Smart data in an enterprise is the infrastructure that is necessary to, realize this integration of both BI worlds and the big data world, so to speak. And such a smart data, how would it look like? It has to have a uniform data encoding. And clearly on the regular world, like the relational world, so to speak, and all of the different types of analytics, there is no uniform encoding. There are a number of encoding schemes that are there. But smart data comes with a uniform, universal encoding. And such a data, once it's housed and all of that stuff, you need to be able to query it, retrieve it, right? And so there better be a very comprehensive, robust querying mechanism. And smart data comes with something like that. And then, of course, once you have such a mass of data, and we are talking about petascale and all data that an enterprise can pull in together, it could be voluminous, right? And so you need to have proper modeling so that you reach out into the far flung areas of the data that you may have amassed. No silo of data should be unreachable, and that all ought to be queryable, and you are able to query it only if there is a good filter, and that filter has to be designed through a proper modeling, right? And so what we are saying is there has to be a comprehensive standardized modeling as well. And of course, there should be standards so that it is every organization can reach out and expect to use it, and there must be vendor tools. And so what are the technologies that actually fill in all these 4 different things that are important, we think? Yeah. So smart data with semantic technology is one way to achieve this. And as I said, the encoding in smart data is something called RDF, right? And RDF is Resource Definition Framework. And many of the folks may be familiar with it. I mean, it is very theoretical, and it has been taught in courses and universities and such, but it has never seen the light of day or not caught fire like the machine learning big rage. But now is the time, as a number of speakers have alluded to, smart data and so on. I mean, as the first speaker talked about cognitive science and so on, there is a little bit of a traction that is building up beyond normal, general, theoretical, university kind of circles. It is getting into real-world commercial sectors. And one interesting thing, as you'll find, is this technology has been in use forever, actually, almost 20, 30 years. And it has been used in some of the most complex applications, like defense and intelligence in the US particularly. And, and on, all the knowledge-based systems that you may be, studying about were one way or another related to, semantics at some level. And it has now garnered all kinds of standardizations, like uniform data encoding at the ground substrate level. And it has the modeling standard as well, OWL, it's called Web Ontology Language. It's a comprehensive, much more robust modeling than your, I wouldn't say relational is robust, but it is not as comprehensive, or it would allow you to model the real world situations, which are ever increasing in complexity. Human beings are prone to kind of making things unnecessarily complicated, and you need a modeling language to mimic all that complexity so that your automated systems can actually follow what you're thinking or what you're expecting to get things out of. And then the querying language, Sparkle, that's also a standard. So you have these fundamental 3 units that are required to deal with mass amounts of data, which is the data encoding, the modeling, and the querying. All the 3 are standard, big standards. There is only one standard. Even SQL cannot claim that. And that is probably news to some of you. But I mean, it is interesting that such an interesting technology is out there, available, scalable, and it's already in commercial production in many, many places. And there are a number of published data sets in these formats that are being put out by major governments, major research organizations that is out there on the web. And this data, like in cancer research or weather data, and that has been talked about in this conference already. So all this data, any of your applications can directly reach in if they are, instrumented dealing with this, encoding, RDF. And you can directly leverage all that data into your applications. And think about the, the differentiation that you can bring to table, right? Health data, I mean, on and on. I mean, more and more it is getting, being that it's a standard, it's out there, more and more data sets are getting published. And published ontologies. I mean, this modeling that I was talking about, when you design your schemas using this ontology or using this modeling language, it's called an ontology. A little fancier word, but it is a little more beefed up schema. But schemas that reflect real world complexity, as I said. I mean, it's not just entity and relationship, relationships themselves can be, multifold. I mean, there are a number of constructs that will allow you to mimic all the fine-grained things that you would expect to see in how you characterize real world. All of that can be mimicked in this, in the system. And sorry, I'm rushing through so that, I hope I'll have a little time for the demo, On the right-hand side, is something that has been talked about by a number of experts and, number of speakers before. But the key thing that I would like to draw attention is that semantic technology is addressing this pyramid from one layer above the data layer, So assuming all data is encoded in this uniform, RDF, then the technology, your algorithmic technology, your code that, folks write, need not deal with, transforming the data into something that your algorithms understand. Now, your algorithms will automatically, and this is, has been written about as being machine understandable code or machine understandable data, right? And so the enormity in terms of efficiency that you gain of, starting out your computation at the level above data, raw data that you probably are collecting through your sensors and your collection systems is massive. Much like what the pyramid would show, the bottom of the pyramid is huge and, it can cover a lot of ground. But all of that to make sense will take a lot of computation. Now you're getting away not having to do all that, and that is a lot of efficiency. So just as an example, RDF, for example, it's the famous triplets. I'm sure most of you all have heard. A triplet is a subject, predicate, object. So all data and every data will be, encoded this way, as a subject, as a predicate, as an object. That's the most atomic unit, and that's how the brain actually is supposed to make sense or, organize data, right? And so, for example, here, Bengaluru is located in Karnataka. So located in is the predicate, Bengaluru is the subject, and Karnataka is the object, right? And so the encoded format will be right below the HTTP, the URI, URL scheme. So all of that, Karnataka and all that. So that is, so once it is encoded this way, all your algorithms will never have to ever worry about whether, it is misspelled, is it from this source or that source, it's standardized. So code reuse can really, take a massive step. And the Sparkle query as an example, like for example, if you're trying to pull out 50 concepts in DVpedia, the syntax, it's very much close to your SQL. Select distinct concept where, the question mark has that subject and a concept and so on. So it's very familiar, similar, easy, and OWL ontology, for example, here I have an example. It's not for you to read, but just to give you a sense of, how complicated schemas, complicated real-world aspects can be brought into an automated world through this modeling, right? So the constructs here, I know this is not readable, but here it is the schema definition for wine, the number of wine, types. If you are, you drink wine, people are familiar with, all the different varieties and all the different flavors and tastes and so on and so forth. There are so many aspects to it, that a wine aficionado will probably not want to ignore, so all of that has to be modeled one way or another. And so some of that will require, such schema, but it might appear to be a little more, involved, but the constructs are pretty logical, like as I said, entity and relationship, that type of modeling for the relational world will mimic only a flat aspect of the real world. Whereas in the OWL modeling language, you have constructs like, transitive property or, inverse property, things like that, that we automatically know, when we say something is happening, you automatically know that not something is happening, is you have a logical place in your mind, how you organize. So, there are a number of such constructs which you readily will understand that they have a place in modeling or mimicking the real world, yeah? So I don't want to get into too much detail here. And when you have all these things, like standards-based encoding, querying, and modeling, and in all of that, smart data becomes real. And what can you achieve with something like that? Like when you are, faced with mass amounts of data, you can ingest any and every data format that you have. All of that can be put into your so-called data lakes. That's a word that has become a little bit popular. And you can put all that data into your data lakes, and it would mimic like a single source on the other end for your upstream data processing, activities. It'll mimic like a single source. Think about the efficiency in terms of all the resources that you would throw at, manipulating this data, assuming that, you are getting data and it appears to be a single source. So interrelationships are already encoded, and the traceability, lineage, all of that is taken care of. Yeah, and such a data, once it's encoded, it becomes an RDF graph because, number of things, be it from different channels, like maybe Twitter data or a weblog data, as long as you say it's a name, I mean, anything that is name will collapse and, it becomes one as a node in a graph. So all the relationships are automatically explicit after that. So that with a comprehensive query, I mean, now we are able to address all the data that is in this connected graph format. So for your machine learning or one-off analytic that you may be planning, in a typical use case or in a typical engagement, you would want to kind of, extract the data that you first of all identify, get it out, do the ETL transformations, and, apply your machine learning and do all of that stuff. Whereas in this case, all you do is a query to draw out that data that you want for your machine learning exercise, right? So, and you don't have to do, ETLs one after the other. I mean, it's just querying, right? So it's extremely, efficient. And it has proven to be scalable to the petascales that, other technologies have claimed. Yeah. So this smart data, and we have our platform, which is kind of architected to use all the aspects of smart data and to leverage, the technologies that are available to, scale up to all these big volumes and velocities and all these things that we characterize, right? At the bottom layer, all data is typed in, for us, we can use HDFS, for example, or not. We use Spark, and so Spark can use all kinds of, formats and so on. But what we layer on top of that is a semantic graph index. And that is the distinguishing, feature that enables smart data, right? And that enables that uniform querying. So no more ETLs once the data that comes in encoded as RDF, right? Be it for your machine learning, be it for your, extensive graph algorithms and so on. It appears, gosh, I mean, I have a 10-minute long demo that actually combines, I might as well run through this demo quickly, and maybe some of you will have questions later on, and then we can talk in the hallways. Yeah, I probably have like 5 minutes or so, right? Is it 5? Yeah. So the business case is, I mean, I want to show it to you that it is real. This seems like too theoretical. I mean, all three different things that are new. Some of you may have heard or may have heard in different contexts and so on, but it is real and it is our product, yeah? So in this demo, what I'm trying to show you is an event management company, one of our customers, wants to identify its target customer groups to incentivize, right? So that they can drive up attendances in, by leveraging the social graph, yeah? So, I mean, it uses all kinds of things. I'll quickly go through this and maybe okay, I mean, it will be very fast because being that it's a fairly involved demo. I'll stop here. This is our user interface. It's out there on the web. I mean, you can freely go to hitdime.com and reach out to this interface. But it appears to be a general visualization tool, right, on the cloud. It does have dashboarding. It does have normal, narrative style analytics and so on, exploratory and such. But it also has, the graph analytics. It also has machine learning built in, and that is the different stuff. And that's what we were trying to showcase. So in this case, this event management company, they have these events that are running, and they want to identify, when an event is conducted on multiple days, what are the repeat users and how are the users that are coming on the first day, how are they influencing the folks that are coming on day 2 and day 3 and so on. And is the social network, has it got to do anything with it? And are there characteristics of these, subscribers or attendees? Are they pointing to whether they are likely to attend or not likely to attend? So we use machine learning as well, and all that. So I will run through, and this will take literally 8 minutes of very fast clicking through various things. So please bear with me, and if someone raises a hand, I will stop, and maybe I can address a question. Yeah. And just focus on the right-hand side for the broader activity that is happening maybe. And so this is the dashboard. So it is initially you start out, first drawing out your question, what question to be addressed for your big data analytics, right? So here they're talking about revenues that are coming in and on different days, So the dashboard is closed, and there is a question about what I just talked about. And so there is an event session. This entire analytical session has happened through a number of point and click things. So identifying the city that is generating more revenue, and out of this city, what are the events that are producing more revenue. And how many days that event that has produced more revenue, and it is on 3 different days, 29th, 30th, 31st. These are all have to do with New Year's events. And so they are trying to figure out on day 1 and day 2, day 3, who are the users, right? So there are 2 colored, node clusters. One is, folks that have attended on day 1, and the second one, the blue, is on day 2. So they are trying to figure out what may be the relationship. So they are bringing in the Twitter data now. So Twitter data bringing in is just as simple as bringing in another set of data. And this new colored node cluster is the data from Twitter. And so they're trying to figure out what is common between Twitter data and day 1 attendees. So it'll so as soon as they are connected, it means they are the same people. Right, and so now they have removed all these orphans so that it declutters the view. And now picking on the clutter data, so they are now bringing in the followers of the folks that are in the Twitter. So you can see that. So now all the users in the Twitter and day 2. So now we have progress from day 1 to Twitter to now to day 2. Yeah, now we are figuring what may be common between these 2. And now here, I'll just pause for a second. So what's happening is, you brought in day 1 data, combined with Twitter data, and figured out, okay, some folks from day 1 are in Twitter, and use those people from Twitter to figure out who their followers are. And from that clutter of, or the list of all those people, we are going into the, the day 2 and trying to draw, connections there. So to figure out, how many people have come, And in order to figure out who may have influenced more, we are trying to figure, the centrality, the popularity of a certain person from the Twitter. And so there are, social networking, all kinds of APIs. So we are using, actor degree centrality here to figure out the centrality of all these people. Just mind you, I mean, it is your, point and click runtime visualization tool. And so once the centrality has run, it gives you the ranking, rank 1, rank 2, rank 3, and so on. So just for further analysis, they were looking at top 3 ranks, rank 1, rank 2, rank 3 by centrality. And now to figure out who may have contributed more to the people that are attending on day 2, right? And so, and in order to further identify why some people may have come, may not have come among the followers, they brought in this geospatial side of it. Maybe event is happening at a certain location, a distance may have played a role. Even if someone wanted to come in, they may not have come because it's too far. And so the geospatial is identifying that, some folks are within 10 kilometers and some others are not. So the ones in the olive green are the ones that are outside of 10 kilometers, and the cyan blue are the ones that are inside 10 kilometers, of the followers that have attended, yeah. So what the finding here is that, the rank 1, rank 2, rank 3, contrary to our expectation, rank 1 is not producing the more number of followers. Rank 3 in this case, or rank 2, was producing more. Why that is the followers of rank 2, majority of them are within 10 kilometer distance from the event, right? So it gives you that, the big analysis that you would normally do. And now they are trying to figure out, how many among the followers are within 10 kilometers versus, outside of 10 kilometers. And so there are various constructs within the user, interaction styles to pull out all these things. Right? So the different number of people from different followers of these ranked people. And so that confirms that, the proximity, the distance has a role to play. So now, so this is up until, what graph analytics and social networking analytics, geospatial analytics will give you. Visually you are able to confirm some things, right? So in addition to that, there are a number of attributes for these attendees that, the data shows some of which has not been used for analysis. And so we figured, maybe machine learning, we could use machine learning to figure out, can we calculate one way or another somebody is likely to come, not likely to come, right? Just to showcase for this demo, yeah? So I'll just continue. So check with machine learning using the role of other attributes, right? In this case, age, gender, and whether they have used discount when they bought the ticket, and the distance also. Yeah, so you can directly launch, either an R or a Spark. That is, we have libraries that connect them back to our HitDime. And so it actually executed and it produced the decision tree in this case. And so that decision tree, the rules are available back to the HitDime runtime, right? And so those rules will appear. And all the machine learning output. So because it has tagged each of the users, all the Twitter users, whether they are likely or not likely, I think that is what has been calculated. And so the prediction for all these users, which is, which users are likely to come for the next day versus, which users are not likely to come. And so that prediction was calculated by the machine